Okay, let's let's review here. Okay, so I'm gonna try to get you guys to help me out here. So review. What you want a pen? Now, I asked you to do some questions from your IBID books. However, I would not be surprised if some of that wasn't completed. Um, so hopefully, well, we'll talk about that a little bit more. Okay, so first things first. What is an acid? Remind me, according to, I think I spelled that right, Arrhenius. What is it? Simplest explanation of what an acid is, or a base. I'm actually putting the quote unquote in there. Donates. And what is another name for an H plus ion? It is a, true, it is a cation, which just means it's positive, but it's also something special. What's that? That is a good way to remember it. That is also on video. They don't think they could hear you say that. It's a proton, right? It's a proton. Okay, once you just doing some learning, right? There's your H ion. If you remove the negative, you're just left with the nucleus, which is the proton. Okay, so Arrhenius donates H plus ions, and there's more to it. Donates H plus ions to what? Right. Aqueous solution. So a great example of something that would do this, the HCl. And you end up kind of like this scenario. In previous grades, we just said an acid was something where the cation happens to be hydrogen, right? We know a little more now. We know that there's a reason why hydrogen has these special properties with relation to water. So when we actually talk about what happens in water in reality, well, first thing to think about is the fact that water itself is in equilibrium. Oh, and by the way, this is a strong acid. I'll talk a little more about strong and weak. This is a strong acid. So what that essentially means is that, you know, there's almost none of this left once you dissolve it. Like, I don't know, like 1%, 99% would be over here. So the equilibrium is pushed far to the right for strong acids. We also know that water itself dissociates into its two ions to a certain extent. This is also in equilibrium. However, the concentration of this, if you were to say, look at the K value, and since this is a liquid, right, you sort of omit it. So you get the concentration of this, concentration of this. Well, what you would find when you look at K values, you would find that this is 1 times 10 to the negative 7 moles cubic decimeter. And this is where the concept of pH comes from, right? It's the negative log of that, which gives you just a value of 7. This number, but positive, right? So it's based on the concentration of H plus when water itself is in equilibrium. So essentially, when I take my acid and I start putting it into water and dissolving it in here and adding more and more, I'm driving up the H plus ion concentration, okay? And reducing the OH minus concentration. So we understand how in an equilibrium, if we're adding H plus, well, that's also going to pull some of this, it gets essentially back to water to a certain point, so it's going to lower the value of OH and drive up the H plus concentration. We all have that? That makes sense? Perfect. Now, what's the limitation of looking at it this way? Why is it a limitation to only consider an acid as Arrhenius said? What's the problem with that? Well, here's the demonstration I was going to do today, okay? And this leads us into Bronsted-Lowry. So if I can get a tube going, I'll show you this next time, or possibly later on in class, if I give you a little bit of time to work, I can maybe get a tube sorted out without cutting my hand off. But if we were to take a tube like this, and we were to put cotton balls in either end, and these cotton balls happen to be soaked with, on one side, concentrated HCl, and on the other side, concentrated ammonia, which is something like 12 molar ammonium hydroxide. And the reason it's this is because if we take pure ammonia and hydrous ammonia, which is a liquid, and you can, like, it is used in farming, for instance, but it's pretty dangerous. It's definitely not something you want to get anywhere near you. It's got an affinity for water, and it's also quite corrosive as a base. It reacts with the water in your body. If it comes near water, it'll just undergo the reaction. Oops, it's not water. It'll undergo the reaction of pulling an H off of water, and then you get your NH4OH, right, in aqueous solution. So that's ammonia right there. Why does this pull a hydrogen off of water? Why does that happen? Well, what does NH3 have? How many electrons around it? I'm going to start drawing them, and I'd like someone to tell me how many. It's not 4. So look at that thing. Why is that capable of yanking hydrogens off of water? Good, it's got unpaired electrons, and that's actually important in a further definition of acids and bases that we have, right? So that H has come from water. So would you consider ammonia to be acid or basic in character? Is that an acid or a base, something that accepts an H+, that pulls an H+ off of water? It's a base, right? Because what it's going to do is it's going to drive up, by virtue of removing hydrogen ions, it's going to drive up the concentration of OH, right? So it's going to make this concentration higher. That concentration gets higher, more H pluses get yanked out of solution, and the H+ concentration drops. This number goes -8, -9, -10, right? It's getting smaller and smaller and smaller. The negative log of that gets a higher and a higher pH. Okay, do you remember all of this stuff? And so on. Okay, as H+ goes down, that must mean OH is going up. Okay, so if we were to take this tube, right, we were to put these in each end, what you'll get is you'll get some ammonia gas coming to the middle. Remember, this is gas, no water necessary. And you'll get some HCl gas coming to the middle. And what do you sort of imagine, actually, I'm not sure exactly if that's right, but what do you imagine happens if you have some HCl gas and some ammonia gas come near each other? What do you expect might be the reaction there? What's that? Yeah, you'll get a salt for sure, but in this case, what will happen is, remember, this NH3 accepts a proton, right, and becomes positive, so it'll jump up to being NH4+ again, right? Okay, and this will be Cl-, so you get an ionic compound, which is a crystal, a solid, of ammonium chloride. Okay, and I wish we could have done that, and maybe we still can, because basically clear gas meets in the middle and suddenly forms a precipitate. Can you have this happening in an Arrhenius situation? Can you have an acid-base reaction without water? No, you can't. So you need to describe acids and bases in another way then, right? That does not require necessarily water to be involved. And that way was this, right? The Bronsted-Lowry definition. This is where we get the conjugate acid-base pairs. How do we describe an acid in Bronsted-Lowry? It's not really that much different, but how do we describe it? Anybody remember? It's in your old notes. Maybe have a look. But that's not the definition in terms of Bronsted-Lowry, though. It's not a definition of what an acid is in Bronsted-Lowry. Remember, Arrhenius just said something that raises the H plus concentration in an aqueous solution. That was his description of what an acid was. Bronsted-Lowry widened it a bit to describe situations where water isn't maybe involved, right? So what do you think? So we have this concept of conjugate acid-base pairs that we talked about. Correct, that's true, we did. We still haven't got to the definition of what is an acid in terms of Bronsted-Lowry. Correct, that's right. It is a proton donor. And it is an proton acceptor. So no talk of water, and hence, when you have this happening, you have two gases reacting, all right? This is an acid, even if it's not at all anywhere near water, right? It's behaving as an acid here. It's a proton donor. Now, it's something we understand to already be an acid, right, from our Arrhenius definition, but it can't, with Arrhenius, you're limited to it only occurring within water, right? So this widens it out a bit. So if you want, right, there's Arrhenius. It describes this world. It's good for most of what we're going to do in the lab. We always pretty much deal with aqueous acids and bases in the lab at our level. However, if you needed to talk about something like this, which we'll do a demonstration of at some point, all right, then you got to jump up to Bronsted and Lowry, and there's actually even a wider definition, okay, where you can describe even certain metals as either being acids or bases. Now, how does that work, and what is that further level called? Do you guys remember? Good. Lewis. Acids and bases. Now the challenge. How did Lewis describe acids and bases? What's a Lewis acid or base? Anybody? Good. Good. An acid accepts an electron pair. Okay. So I mean, like H plus is a good example. So let's say we have something with an electron pair. Free electron pair, and we have something that can accept it, in this case H plus, right? H plus will associate with this electron pair, so it's donating its electron pair over to hydrogen, okay? So we're still talking about hydrogen, same as we were before. However, there may be some other things that are described as Lewis acids as well that are not hydrogen, and we get something like this at the end of the day, okay? So in this case, right, here's your Lewis acid, and here's your Lewis base. So if an acid accepts an electron pair, the base is an electron pair donor. Okay, let's see if there's a good example that, yeah, okay, let's try this. Okay, so let's see if we can do an acid base without actually even having any hydrogen itself involved. So if we had, say, something like, what was this again? What's that called? Yeah. Plus, we might have something like this, which is a little bit hard to understand, but let's see if we can. What element is that? Yeah, we talked about this before. How many electrons around a boron? Outer shell. 3. And it turns out that there's a stable version of this called Boron Trifluoride. Right, remember, We look at our electron shells. It'll match up like this. Now this is stable. It does not obey the octet, but it is stable. Now, which one of these is an electron pair acceptor? Yeah, there's empty parts of this shell, right, that can accept these electrons here. And what you would, I guess, end up with in this case is something that looks like this. And I'd like to say the name of this is ammonium boron trifluoride, but I'm not exactly sure. Ammonia boron trifluoride. And that is exactly what it's called. But look, this is, you know, a base in terms of Lewis. This is an acid in terms of Lewis. No H plus necessary. So boron trifluoride is a Lewis acid. It has acid properties and behaves like an acid. Okay, are you good with that? Does that make sense? You will be asked to identify these things when you're, you know, when you're tested on this stuff. Okay, let's try one more thing here. What if I were to have, what if I were to show you this? Here is something. Okay, this is an iron ion, right? Iron 3, and it turns out this actually behaves as a Lewis acid. Okay, so what it'll do is if we have some water around, okay, water will be strongly associated, right, with this positive ion because water is polar and it's got these bare electrons hanging out on it. It will start to associate, and lots of waters will be able to surround this iron ion. And eventually what you get is you will get something that looks like this. You'll get this complicated ion here that looks like this. Iron with 6 waters attached to it, and it's still got its 3+ charge. Okay, so this is like a weird looking ion, right? And this can then react as any 3 positive ion would react. And it has a name. It's called the hexa aqua iron 3 ion. I guess you can see where that name comes from. Hexa aqua iron 3 ion. This accepts many, many, many electron pairs and therefore is a Lewis acid. So metal ions are actually considered Lewis acids because they can accept electron pairs. Okay, so that's a quick, you know, review of what we've talked about before. One other thing, just going back to Bronsted-Lowry. Is the concept of acid-base pairs. So let's say you have something like this. Okay, let's go like this. And what you should get out of this situation is, well, you'll actually get this. Okay. So if we look, this is the proton donor here, right? And this is going to accept a proton. Now, in our review, we didn't talk about this ion, all right? This is sort of the more realistic view of what's going to happen if we dissolve an acid in water. This is the hydronium ion. It's what really gives us acid character. Although we don't often have to go into the detail of talking about it like this, for this demonstration it makes sense. So this, in this case, is the acid, and this is the base. And then conversely, there's going to be a conjugate pair, right? So now if you look over here, in the return equilibrium, which is very limited, it's very small, so maybe this wasn't the best example, but in the return equilibrium, this hydronium is now donating its H+, right, back to the Cl- over here. So in this case, this is the conjugate acid. So here's an acid-base pair, or base-acid pair. Now this is the acceptor of hydrogen, so this is now the base. So this is your conjugate acid-base pair. So what you would do is you'd say this is a pair, and this is a pair. Okay, and you might be asked to identify those on some questions. Okay? So that's that. That's our definition part. And then let's identify. So you have a little sheet there. That has a big list of acids and their strengths in descending order. So the one at the top of the list is a very, very strong acid. It's perchloric acid. So we'll pull that out and have a look. And that's hydrogen with the perchlorate ion. Okay. So if we talk about a conjugate acid-base pair here, as they're sort of doing, what would be the conjugate base of this? Good. Okay. So here's this acid, and here's its base. Now, looking at this, looking at ClO4, what type of atoms are there in ClO4? What property do they have that might lend itself to making this a much stronger acid than, say, acetic acid? Why is this so strong an acid? Good. They're all strongly electronegative. So essentially what that means is the hydrogen can't really hold its electrons to itself nearly at all. So interestingly, and you'd think it might be the other way, you'd say like, well, maybe something that's really electronegative holds this on here very well, but it actually turns out that this pulls the electron away and hangs this out. And I suspect it has something to do with the geometry of the way this acid is set up that makes it extra strong. That H plus is highly accessible to any base really that comes along to grab it, right? So if you were to just dissolve some of this in water, we can expect that it's going to very strongly react, right? Hydrogen is going to associate with the electrons over here, free electrons on the water, and you're going to get your perchlorate ion, your hydronium ion, and you're going to find that this equilibrium is like way over here. Okay, so that leads us to a definition. What is a strong acid? Well, strong acids have an equilibrium which lies very far from products. Okay, essentially no undissociated, I don't have enough room to write dissociated, but undissociated, I do, no undissociated acid remains, basically. Okay, so it's all over in this form. Does that make sense? You guys follow that? Okay. So this tends to happen with very electronegative anions. Okay. We're lucky we don't have to talk about Kas or anything like that, but if we wanted to, right, if we wanted to look at the K values here, we would just see that the value of products, right, is much higher than the value of reactants, right? The concentration of is very high. So if that's correct, then K is much above 1, right? So if we have 1, our K value is much higher than 1 for a strong acid. And when we're talking about an acid, it's not just a K value, it's a Ka. K is very high. Now we can like roll down to a weak acid. So let's find a classic one. Let's talk about acetic acid. Let's look at how it's a bit different. Okay. You know, it would help actually if we had some K values to compare to, but we can maybe look those up a little bit later. So that is like this. It's an H attached to the acetate ion, which is C2H3O2. And what would its conjugate base be? Good, which is called what ion? I just said it. Yeah, so there's its conjugate base. I don't know why it has that name. I'm not sure. Okay. Now, if you can look up the name origin of acetate if you want, for sure. If we put it in here, now we get a true equilibrium, right? In fact, I'm not exactly sure, but I believe this equilibrium actually is less than 1. Okay? Don't quote me on that, but I believe it is. These are all aqueous. Well, actually, sorry. So if I look at this, right? This is just like an organic molecule. There's some oxygen there, but there's no. It's not like with perchlorate, right, where you've got 4 oxygens and a chlorine. You've got carbon and hydrogen, which are not very, electronegative. You do have some oxygen, but it's kind of already paired off. So yeah, this is hung out to dry a little bit, and it can be pulled off. All right, but it's I guess a much stronger bond, a harder bond to break than in other acids. Okay, so just you can roll down the list and you can take a look at how that all works. The other side of this scale, kind of got to go to the bottom. Now we're going to go to basic character. Right at the bottom, the most basic thing that you can probably get is actually the hydroxide ion itself. Right, it's an extremely strong proton acceptor. If we try to figure out what it looks like, what does it look like? Let's just see here. So there's that. And we're going to yank an H plus off of here, right? So it should actually look like this, right? Well, that is something that if a proton ever comes near, it's just gonna grab it, right? And away we go. So yeah, I mean, I think that's essentially all we really need to talk about. Right in the middle of these guys, between acid and base character, you'll find your neutrals, like water. Okay. Yeah, so halfway down the list. Are there any questions about any of that? Okay, let's end that then for now.